Welcome to Visual Algebra Lecture 1.5, Cayley tables. In this lecture, we'll learn about a new way to visualize finite groups. In some sense, a Cayley graph, which has been central to all lectures so far, is a type of group calculator. It allows us to quickly compute the product of two elements by just concatenating paths. Another useful tool is very similar to something that we all learned about in grade school. Now, I'm assuming that as a kid, you, like me, was in a classroom and there were big multiplication and addition tables on the wall with the numbers like 1 to 10 or 1 to 12. That's what this is. We can do the same thing with a group, but now we use the group binary operation. So here's the Klein 4 group, and this basically tells us how to multiply two elements together, like V times H is R. Here is the triangle symmetry group, and here are the 6 elements, and R times F is RF. R squared times F is R squared F. This does the same thing. We will call this a Cayley table. We're not using the word multiplication because sometimes the binary operation can be addition. First, we have to make a notational convention. Since AB and BA are generally not the same, we will say that the entry in row A and column B is AB rather than BA. So RF goes right here, whereas this entry is F times R, which is R squared F. Cayley tables can reveal patterns that are otherwise hidden. And sometimes these patterns only appear if we arrange elements in a certain order. In order to illustrate that last claim about patterns appearing in certain Cayley tables, I want to introduce a new group to you. This is called the quaternion group, or just the quaternions. This is a very standard group. It's in pretty much every algebra course and textbook, introductory that is, unlike some of the examples that we will see in this lecture series. And here are 4 Cayley graphs of it. And first, it's in no way clear that these even represent isomorphic groups. They all have certain similarities, like they all have red 4 cycles and blue 4 cycles. So it's not like the triangle symmetry group where we had that one example where we got a hexagon with two generators and another one that looked nothing like that. Notice how each one of these highlights different structural properties. The first 2 Cayley graphs emphasize the similarities and differences between the quaternions and the square symmetry group, which we saw a couple lectures ago on presentations. I think I showed you a Cayley graph that looked just like this, but instead of those blue arrows being 4 cycles, they were 2 cycles, so just undirected edges that were connecting these pairs of corner vertices. If you lay this out differently, it looks like this. And the square symmetry group would have, instead of these 4 cycles, we'll just have these 2 cycles or undirected edges connecting these things. This one is something we haven't seen before, and this one has an extra generator, which is definitely not needed. If you remove these blue edges, you get a connected diagram. But as we'll see, it's convenient sometimes to have this extra generator. Now, notice that I have not told you what this group is. What are the actions or the elements? And it turns out that this is the first group that we will have seen that does not represent something concrete. At least it's not obvious that it does, like the symmetries of an object or the rearrangements of a certain puzzle or a game. This is going to be an abstract group. The group Q8 is, well, it consists of the so-called imaginary numbers I, j, and k and their negatives, and plus or minus 1. Now, what do I mean by that? So we all know the imaginary number I, which is the square root of -1, or I squared equals -1. And so imagine that we have j and k that are analogous. So j squared and k squared are also -1. Well, now I have to tell you how to multiply I, j, and k together. And here's how we do that. We will arrange I, j, and k in a circle, and we'll put arrows in the so-called increasing order. So I goes to j, goes to k, goes back to I, and put a plus there. This is the positive direction. So if we multiply by any two of these numbers, the answer is the third, and it's positive. So I times j equals k. J times k equals I, and k times I equals j. Now, if we multiply in the reverse direction, the result's going to be negative. So you can either do that in the reverse direction and make a negative, or you can draw a second version here. Say I times k equals negative j, and so on. So this might remind you, if you've taken vector calculus, and not too long ago that you've forgotten this, but if you've taken vector calculus and you've seen the cross product, then you've learned about the vectors. This is I, this is j. These are like the unit vectors in each direction. This is k, and I cross j equals k, and j cross I equals negative k. And the cross product is technically the cross product of any two vectors, if you remember right. And if you don't or have not seen this, that's totally fine. You put the I, j, k vectors here, and then you put, let's say, a1, a2, a3 here for the first vector. So a cross b is this, and then b1, b2, b3 right here. So if you do this for I, j, and k, for example, for I cross j, I is 1, 0, 0, and j, sorry, that's not 2, is 0, 1, 0, and then you take the determinant of this. So if you don't remember what the determinant is, I'm not going to explain it to you, but just think that multiplication of these things behaves just like the cross product of I, j, and k in vector calculus. Here are two possible presentations for the quaternions. We can say it's generated by I, j, and k, such that I squared and j squared and k squared and I times j times k equals negative 1. This encodes the fact that I times j equals k, and k squared is negative 1. Now, k is not needed because I times j equals k, so this is not a minimal generating set. So we could write it as I and being generated by I and j, where I to the fourth and j to the fourth is 1. So let's go down here, and I is red, 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 red. I to the fourth, I guess, is that. And j is blue, 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 blue. So those things raised to the fourth are 1. And then we have to say how the red and blue arrows interact. So I, j, I equals j. So that means red, blue, red equals blue. Now, I don't know about you, but I would prefer this first generating set, because when I look at this, if I'd written this with A and B instead of I and J, it's in no way obvious how many elements is in this group. And it's not necessarily obvious in here how many there are either, but here I wouldn't even have the language, to write down a K if you hadn't told me that there was one. What is I times J? The idea is you can write everything in terms of I and J, but I think it's just more useful to think of this as being generated by I, J, and K. And also, one quick comment. Negative 1 is not a standard. For a general group, you can't just write negative times the identity. So it's a slight abuse of notation here to do this, but I think it's clear from the context what this is. And in this case, it's okay because we understand that this is the group consisting of these 8 elements right here. So here is a Cayley table. And right now you look at this and, what do you notice? Well, the square of every element is either 1 or negative 1. There's not much else. Or at least I don't see much else. But remember how I said that some patterns in Cayley tables only appear if we arrange elements in a certain order? So instead of doing 1 I, j, k, the positives followed by the negatives, negative 1, negative I, negative j, negative k, I'm going to group the 1s together, then the i's together, then the j's, and then the k's. What do you think is going to happen? Any guesses? Okay, this is your last chance to guess before I show you. Well, look at that. What do you notice? Well, I hope you notice that this is basically the Cayley table of V4 if you squint your eyes and look at 2 by 2 blocks. And here's another way to write that. So plus or minus I times plus or minus j is plus or minus k. What does that mean? That means if I multiply, or if I take one of the i's, plus or minus, and I multiply by one of the j's, I will always get one of the k's. In other words, I times j is equal to k, or one of the i's times one of the j's is equal to k up to psi. Notice that this edge that I've added, this green edge, is -1. Again, it's not needed, but it helps connect up these pairs that appear in this table. Collapsing the group Q8 in this manner reveals the structure of V4. This is an example of taking a quotient of a group by one of its subgroups. In this case, the subgroup generated by -1. We will return to this. Basically, what's happening is the elements in this smaller shrunken table are plus or minus 1, that's these nodes, plus or minus I, plus or minus j, and plus or minus k. Notice how the elements are the identical fragments of this subgroup that appear throughout its Cayley table. That is not a coincidence. And what that's basically saying is that if you, how do I want to say this? If you collapse these nodes, if you consider these nodes to be single elements like we do in this table, we collapse them, we get this Cayley graph. So we can collapse within the table, or we can also collapse in the Cayley graph. And this, a little bit of a preview, is going to define a map from, it's called a quotient, from the group Q8 to the group V4. And maps between groups is the topic of section 4, or chapter 4 in this video series and in my book. But we will first return to quotients at the end of chapter 3 before we actually see the map that's involved. That said, one thing that I really like to do is sprinkle in a lot of intuition of advanced concepts that are coming so they seem natural when we get to them. And this is one of those things, that one of those examples of such concepts. I've already done this already without you knowing it, and I'm going to do a lot more. Here's another example of a quotient. This is the 3 light switch group, which we can also write with these binary strings and add component-wise modulo 2, as I talked about in an earlier lecture. I think that was lecture 1.3. So here is a Cayley graph of that. And if you squint your eyes, this one, the colors are not quite as distinct. I mean, I've tried to group the similar colors together, but if you squint your eyes, you should also see the structure of the table, or of the table of the Klein 4 group by these 2 by 2 blocks. But there's also something you can see. So if you take this upper 4 by 4 block, you look at that, you say that if you ignore everything else, this thing is an actual subgroup. These are 4 elements that when you, in this case, it's not multiply, it's add them. Binary operation is addition mod 2. If you just take these 4 elements, they form a group. Anything in here plus anything in here is still in there. So this is a subgroup of the 3 light switch group. And if you look at this, you're basically ignoring the last coordinate. So this is the subgroup consisting of the first 2 light switches. So when you ignore the 3rd light switch. If you don't know what I mean by the light switch group, again, I talked about this in, actually I think in the, maybe, I talked about it in 2 different lectures. I don't remember offhand which one it was, but it was a little bit earlier. So here's the Cayley graph, and here's the Cayley table. But now let's go back to, again, this is a subgroup, but let's go back to the idea of a quotient. So if you look at these 2 by 2 blocks, these pairs, they all differ in only the first coordinate. It's the last 2 coordinates where they're the same in. So if we call this block here hyphen 0, 0, I mean, this is the 2 elements that start with anything and end with 0, 0. These are the 2 that start with anything and end with 1, 0. These start with anything, end with 0, 1, and these start with anything, end in 1, 1. Then this Cayley table, which has a structure of V4, consists of these elements here. So if I take anything that ends in 0, 1 and I add it to anything that ends in, say, 1, 1, then I certainly get anything that ends in 1, 0. Now, what is this? There's actually another quotient involved. If I squint my eyes even harder and I look at these, so now I will write on top of this because I won't be here too much longer, or I'll leave this. But if I look at this 2 by 2 or this 4 by 4 block, or these 2 4 by 4 blocks, you squint your eyes, there also is a subgroup structure, or there's a group structure here. And that's given by this. So things in here are the ones that end in 0. Things in here end in 1. Things in here end in 1. And things in here end in 0. So this has a group with just 2 elements. So if you add anything that ends in 1 to something that ends in 1, you get something that ends in 0. So this is a quotient. And what you're actually seeing here is one of the isomorphism theorems, which is a fundamental result in chapter 3 in detail. It's saying that if you take this group and you take a quotient and then you take another quotient, because you can look in here and squint your eyes and say, hey, look, there's this block that ends in 0, this block ends in 1, this ends in 1, this ends in 0. If you take a quotient and then again you take a quotient, you take the quotient of a quotient, that's the same thing as starting with the original group and just taking a larger quotient. These 4 by 4 blocks. So that's one of the isomorphism theorems. So more on this in chapter 4. Okay, now we're ready to prove something. I claim that an element in a group cannot appear twice in the same row or column of a Cayley table. Seems straightforward enough, right? But how would we prove something like that? Let's start by supposing that in row A, the element G appears in columns B and C. So what does that mean? That means that in row A, columns B and column C, we have the element G. So that means that A times B equals G, but also A times C equals G. Now let me point out that I'm not starting by saying, for sake of contradiction, suppose this is false. We could do that, but typically it's good to avoid proofs by contradiction if there's a way to, and that's easier, and many times the direct proof is a little simpler. So what I'm going to say is, suppose this happens, and then I will conclude that B and C have to be the same. So there's no contradiction there. It's just saying if this happens, then B equals C. And there we get uniqueness right away. That's typically a little bit cleaner, though sometimes you can't really avoid contradiction. Okay, so got this. We have AB and AC equals G. Here we go. So now what are we going to do next? Remember what we're trying to show? We're trying to show B equals C. Well, we're basically there. We just multiply both sides by A inverse on the left. So if we multiply everything on the left by A inverse, we get A inverse AB equals A inverse G, which is A inverse AC, and that means that the A's cancel here, so B equals C. Thus, G, or any element, cannot appear twice in the same row. And once again, verifying that G cannot appear twice in the same column is analogous. I want you to do this yourself. It basically is the same thing, but you write, well, I'll let you think about how it's different. It's good to do. You can watch me do dozens of proofs, and understand every single one of them, and you will not be able to do a single one when you pick up your pen the first time and try it. You have to do them. So please pause your video, try this, write it out. There's something about writing it out that it gets those neurons firing that is not the same as if you think about it in your head or just watch it. It's like trying to learn to serve in tennis by watching videos, or trying to drive a stick shift automobile by watching videos. You can do it as many times as you want, but you have to actually get the muscle memory to do it yourself. Let me now pose you a question. Suppose we have a table where every element appears in every row and column exactly once. Is it necessarily a Cayley table for some group? Well, the answer is no, because we need there to be an identity element. But what if I also say that there is an identity element? Well, a table where every element appears in every row and column has a name. This is called a Latin square. And here are 2 Latin squares on a set of 5 elements, and both of them have an identity element E. That is an element that when you multiply by anything on the left or on the right, you get that element back. So are these necessarily Cayley tables of a group? I'm not going to tell you the answer. You'll have to wait for the next lecture. But it's a fun exploratory exercise to see if you can construct a Cayley graph for either of these Latin squares. If you can, then you should be able to write down a graph with 5 nodes and label them with A, B, C, D, and E. And if not, what goes wrong and why? And the way that I'm phrasing this, it's suggestive that the answer is no, right? I probably wouldn't give you 2 examples where the answer is yes. So yes, the answer is no for one of these. I'm not going to tell you which one, but I encourage you to explore it. I think it's a worthwhile exercise, and we'll see the answer in the next lecture when we finally, once and for all, give the formal definition of a group. And we'll see, and the fact that we can't define a group with just a Cayley table or a Latin square like this. And we'll actually see a similar example of something that goes wrong if we try to define a group with just a Cayley graph. Really hits home for why we need the formal definition of a group. So stay with us.